In this video, we're going to talk about some properties of functions. The first property is a symmetry property. So we've actually already talked about these, even and odd functions. Okay, so that means they have even symmetry or odd symmetry. These are symmetries we've seen before, but we're going to see a different way to check for, slightly looking different way to check for it. So we say a function is even if for every x in its domain the number negative x is also in the domain. With the same y value. So f of negative x is equal to f of x. X and negative x have the same y value. Okay, so that's what we call even, an even function. And what this means is that it's going to be symmetric about the y-axis. Okay, so this is equivalent to the y-axis symmetry. Okay, so if I draw you a little picture, okay, so if I have x over here and negative x over here, their y values are going to match. Okay, so this y value is f of x and f of negative x. Okay, so like a parabola centered at the origin would be an example of an even function. Okay, maybe let's just put this in a box because it is the most important bit. Okay, now a function is odd if for every x in the domain, okay, negative x is also in the domain, with f of negative x is equal to minus f of x. Okay, so this means that the y value of negative x is negative the y value of x. Okay, so this means that the y values are negatives of each other. Okay, now the odd function is the origin symmetry. Okay, so these ones are going to be symmetric about the origin. Okay, so again, in a little picture, if this is x and this is negative x, if I have a point up here with the y value f of x, I should have a point down here with the y value negative f of x. Okay, so just the negative version. And like a cube root is an example of this, or cube, sorry. So this example is y equals x cubed. This example was x squared. Okay, but so you get these points. So x and y gives a point at negative x, negative y. Okay, that's the same as what we did before. Okay, it just looks a little bit different. Now, if n is an even number, okay, and you want negative x to the power n, it's always x to the power n, because this is negative 1 to the power n times x to the power n, and negative 1 to an even power is just positive 1. Oops. So that's always x to the n. So that means that any polynomial with an even power like that, only one, so a monomial with an even power, is going to be an even function. Okay. Now, if you have an odd power, then you're going to get negative x to the n. So that's going to give you an odd function. Okay. So for example, this function here is going to be an even function because all the terms are even powers. Okay. Now, just to point out, this 1 is actually 1 times x to the 0, and 0 is an even number. Okay, so that is also an even function. So if you sum or if sum or difference, maybe I should write the sum or difference, okay, of even functions is also an even function. Similarly, the sum or difference of odd functions is also an odd function. Okay, let's do one example. So we're going to determine if this function is even, odd, or neither. Now, if you remember when we did symmetry, the y-axis symmetry and the origin symmetry, we actually had to test them separately. Okay, here we can test at the same time because both of them depend on f of negative x. Okay, so that's what we're going to start with. So we just look at f of negative x. So that means that everywhere I see an x in my equation, I'm going to plug in negative x. So this is going to be 4 times negative x all squared over 3 times negative x plus 1. So negative x squared is just x squared. So I get 4x squared on the top. But down here I have negative 3x plus 1. Okay, now this is not equal to f of x. Okay, so that means that this function is not an even function. Okay, but it's also not equal to negative f of x. Okay, that would look like negative 4x squared over 3x plus 1, which you could write as negative 4x squared over 3x plus 1, or you could write as 4x squared over negative bracket 3x plus 1, which would be 4x squared over negative 3x minus 1. Okay, so this minus here, so it's similar to what we have, except here we have a plus and here we have a minus. Okay, so it's not the same again, which means that it's not, actually let's write it over there. Okay, so all of this means that it's not an odd function either. Okay, so this function is neither even nor odd. Okay, but you can see that all you have to do is look at f of negative x. If it's equal to f of x, you get an even function. If it's equal to negative f of x, then you get an odd function. Okay, so you just have to look at one thing and you get both of your answers at the same time. Okay, I'm going to leave this example for you to do. Okay, so you check if it is even or odd or neither. And let's talk about some more properties for functions. Okay, so another thing we talk about often for functions are whether they're increasing or decreasing and whether they have maxes or mins. Okay, so we say a function is increasing on an interval I if for any x1 and x2 in I, where x2 is bigger than x1, so this just means that we're moving to the right. Okay, we're just picking one at random to be bigger. Okay, so x2 is the bigger one. So if we have that the y values are getting bigger, so f of x1, so x1 is the more left one, is less than f of x2. Okay, so another way to say this is the y values get bigger as we move right. Okay, so if the graph is doing that, then you know it's increasing. Okay, decreasing is just the opposite, so we're still moving right, but here f of x1 is actually the bigger one. Okay, so that means that the y values, the y values get smaller as we move right. Okay, let me just draw a little picture for each. Okay, so maybe here's x1, here's x2. So remember x2 is the bigger one. So if it's increasing, that means the function is getting bigger. Okay. If it's decreasing, it means that the function's going down. Okay, so it might look like that. So the y value up here, this is f of x1. Okay, and down here, this is f of x2. Okay, so the y value is smaller than it is from the one on the right. Okay, and now we say it's constant if the y values are actually the same. Oops. Okay, so it would be constant if the y values stay the same. Over the interval. Okay, so that's going to look like a flat line. Okay, so something like that. So maybe here's x1, here's x2, and notice that their y values are the same. Okay, so then we would say it's constant. Now, we can have what we call local minimums or local maximums. And then I'll talk about what an extremum is. Okay, so first of all, a function f has a local minimum at x equals c if there is an open interval containing c so that for all x in the interval, say I, c has the smallest y value. So we have f of c is less than or equal to f of x. Okay, so f of c is the smallest y value. Okay, then we would say that f of c is a local minimum of f. Okay, so the y value is actually the minimum. Okay, so notice that we say at. Okay, local minimum at x equals c, but the minimum is actually the y value. Okay, similarly, well, let's, maybe I don't want to use pink though, but I will switch colors. Similarly, a function has a local maximum at x equals c if there is an open interval I containing c so that for all x in the interval we have f of x is the one that's smaller. So f of c is the biggest. Okay, so if f of c is the biggest, then we have local maximum. And again, the local maximum is f of c. Okay, so not the x value, but the y value. Okay, now a local extremum is just a local max or local min. Okay, so if we don't know if it's a max or min, but we want to refer to it, I wrote max twice, then we would say extrema or extremum. Okay, let's go back to pink. So local maximum and local extremum. So that's the idea behind the local extremum. Okay, so you're either the biggest y value or you're the smallest y value in the interval. Okay, let's look at an example because this might make it a bit more clear. So here's a graph of a function. Okay, where would it be increasing? So if you want to tell where increasing or decreasing, you always want to look to the right. Okay, now if it's increasing, it should be going up to the right. So it looks like from -1 all the way up until 1 that the function goes up as we go to the right. Okay, so on this part it's going down, and also on this part it's going down. Okay, so it's going to be increasing on the interval from -1 to 1. Okay, it's going to be decreasing everywhere else. Okay, so it looks like that it continues in this fashion. Okay, so this is going up forever, this is going down forever, but we always move to the right. Okay, so it's coming down all the way until it gets to -1, and then after 1 it continues to go down as we move to the right. So it's going to be decreasing on the interval from -infinity to -1, and then again from 1 to infinity. Okay, now where would there be a local maximum? Okay, now it says at. So you want to look in an interval where the y values are the biggest. There's a biggest y value. Okay, now I think here there's a maximum because I could take my interval. Okay, it doesn't have to be a big interval, but let's say I take my interval like this. Okay, so that's my interval I. In this interval that contains the number 1, okay, x equals 1, f of 1, maybe I don't want to write that like that. So this point has y value 4, which is f of 1, okay, and it's going to be the biggest in that interval, right? All the other y values in this little interval are smaller. It doesn't matter that the y values over here are bigger, okay? It's local. Okay, we have a different idea if it's the biggest overall. Okay, but here it's just the biggest in its little neighborhood. So in the neighborhood around x equals 1, x equals 1 has the biggest y value. Okay, so there's going to be a local maximum at x equals 1. Okay, and in fact, the local max is, okay, y equals 4. Okay, so it's always the y value is the actual max. Okay, similarly, there's a minimum down here at 0. Okay, because I can take an interval, doesn't really matter. Let's say I go all the way to here. Okay, so maybe this is my I for the minimum. But you can see that the value at x equals 1 is the smallest y value. Okay, so there's going to be a minimum at x equals -1. Okay, but the local min is y equals to 0. Okay, so that's the idea behind the mins and the maxes. You look for peaks. So a maximum, okay, is a peak in the graph, whereas a minimum is going to be the bottom of a valley. Okay, so they often call them peaks and valleys. Now you can also talk about rates of change, average rates of change, and we deal with these on a daily basis. Okay, so imagine you're driving. Okay, S of t is giving the distance in kilometers that you've traveled after t hours. Okay, so if S of 2 was 180, that means that in 2 hours we traveled 180 kilometers, right? So the T, so T equals 2, that means 2 hours. So the T units is in hours. And S of 2 equals 180 means that the kilometers. Okay, so 180 is the number of kilometers that we did. Okay, so S of T is the distance. Okay, so then what was our average speed? So the average speed would be the speed you went on average. So over that interval, it's the distance traveled, okay, in an interval, divided by the time it took. Okay, that's how we're going to get the average. So here, that's 180 kilometers over the 2 hours that it took. So that's going to be 90 kilometers per hour. Okay, that's our distance, that's our average speed over that interval. Okay, now it doesn't mean that we traveled that speed the entire time. Maybe we went sometimes fast, sometimes slow. Okay, but overall, in order to get that distance in that many hours, that must have been our average speed. Okay, now this is the idea behind the average rate of change. Okay, so when you're talking about average rate of change, you're always talking about over an interval. Okay, so you're going to be given an interval from A to B. Okay, now the average rate of change, okay, I'm going to call it ROC, okay, on the interval from A to B is going to be the slope. Okay, so like we did up here, it's the distance over the time it took. So that's the length of that interval. So it's going to be, so if we have here y is equal to f of x, okay, it's going to be the change in y over the change in x on the interval. Okay, so this is change in y on the interval divided by the change in x. Okay, also on the interval. Okay, so here, because I have a notation for the function, so we go the y values. What's the change in the y values? Well, that's going to be f of b minus f of a, right? It's the y value at b minus the y value at a. Okay, and then I'm going to divide that by the change in the x value. So that's b minus a. Now this might look familiar because it's similar to the slope. Okay, now note here, okay, a and b are not the same. Okay, so we have a non-zero interval. So they're not equal. Okay, now if we use that to find the average speed like we did up here, it's going to be f of 2. So our interval, maybe I should write the interval, is going to be, so we started traveling, and after 2 hours we were 180 kilometers. So it's going to be over 0 to 2. So from 0 hours to 2 hours. So it's going to be f of 2 minus f of 0 over 2 minus 0. And f of 2 was 180. F of 0 is the distance after 0 hours is going to be 0. Okay, so notice that we get the same thing. Okay, so without even knowing it, we were already using that formula. Okay, so that is the average rate of change. Let me just put it in a box here because this is important. So you're always going to be given an interval. Okay, now I'm going to leave example 2 for you to do so you can practice using that formula. And we're going to talk about something that's related, okay, but seems slightly different. So the secant line, so let me just draw a function first. Okay, maybe it looks like that. Okay, so maybe this is the function y equals f of x. Okay, and then I'm going to put maybe a here. And b here. Okay, so that means that this point here is f of b, and this y value is f of a. Okay, so the secant line is going to be the line that connects 2 points. Okay, so it's going to look like a straight line that goes through those points. Okay, so that is the secant line from A to B. Okay, so that's the picture, that's the idea. So let's define it more formally. Okay, so if we have 2 points, A, f of A, and B, f of B, okay, on the graph of y equals f of x. Okay, so they're on the graph of f. So this, remember, A is the x value, f of A is the y value that goes with it, using the equation. Okay, then the line connecting these points, maybe I should say the straight line, connecting these 2 points is called the secant line. Okay, so that's how you find a secant line. So we often want the slope of the secant line. Okay, so the slope, remember, is going to be the rise over the run. Let me just get a new color here. It'll be green. Okay, so the rise, so what we're going to do is make a little triangle here. Okay, so this bit is the rise, and this bit down here is the run. Okay, so the slope, I'm going to call it m sec, okay, because it's the slope of the secant line is always the rise over the run. So here is the difference in the y values. So that's going to be f of b minus f of a over the difference in the x values, which is b minus a. Now you might notice this is the same as the average rate of change on the interval from a to b. It's the exact same thing. So these things are very closely related. If you want the slope of the secant line, it's from a to b. It's the exact same as the average rate of change on the interval from a to b. Okay, now often, instead of using a and b, we're going to replace b with, so let me just draw a new picture, I think, here. So often, instead of going from a to b, we're going to go from x and then some bit away from x. So we call it x plus h, x plus a little bit. Okay, so if our function, I don't know, does something like this. Okay, so this y value is f of x. Okay, this y value over here is f of x plus h. And the secant line is going to look something like this. Okay, so again, you want the slope of this. It's the exact same thing. So m sec is going to be f of the x plus h. That's our new b. Okay, so maybe I'll just write, so down here we use x for a and x plus h for b. Okay, but basically it's the same. So it's going to be f of x plus h minus f of x over x plus h minus x. So that actually simplifies to f of x plus h minus f of x all over. Now on the bottom, the x and the minus x are going to cancel, and I'm just going to get the h. Now, we've seen this before, right? This is the difference quotient. Okay, this is why we practice stuff like that. This is used a lot in calculus. You often want the slope of the secant line. And then later the tangent line. But you want to use the secant line to get it. So this is a difference quotient, and it's the slope of the secant line. So we're seeing things repeated over and over. Now again, I'm going to leave example 3 for you, but it's actually, so now we're looking for the slope of the secant line, but it's the same function and the same interval as example 2. Okay, so keep that in mind when you're working on it. Might be pretty similar. But I'll leave that for you to do. Okay, secant lines are very important, and we're going to be simplifying quite a lot of them. So those are some properties for functions.